Hey guys, and welcome to day 18 of Derivative a Day. So here I have our function, and I'm wanting to try something today that we haven't tried on this channel before. And it doesn't directly have anything to do with the derivative itself, but I'm wanting to plot and graph the function after the video. So we get to have a bit of a look at how our function and its derivative compare, and even just look, because I can imagine some of these functions we're deriving would look a little bit crazy. So yeah, that's not what we're going to do at the end, but let's just jump right into it. So we have sine of x, and within this, our function sine of x, we have log of x over cosine of x. And before you pause this video and try it yourself, I want to just ask you guys, try solve this without actually using the quotient rule. Because as I said, well, on Integral a Day, actually I haven't said it on this channel yet, whenever I'm dealing with trigonometric identities, at the moment, I'm not actually going to be solving them during the videos for the first time. I solve them before so I can find the quickest and best way to solve them before the video and show you guys that. So I've already had a crack at this and I already know what my answer is, but I found a way to not use the quotient rule here, so try that yourselves. But yeah, now let's get into it. We're going to need to use the chain rule, which we all, oh, what am I doing? Oh yeah, so we're going to need to use the chain rule, as we've all used plenty of times before on this channel. If you're new, definitely just go back to the first video and work your way through. That way you're like learning all the things, and just do one a day, and eventually you'll catch up. If you want to catch up, so you're doing them daily with us, just do 2 a day maybe. Especially at the start, that won't be all too hard. But yeah, so we use the chain rule here. So our derivative can equal sine. Well, derivative of sine is cosine. Oh, and this is where we're going to take this and use an identity. 1 over cosine x is equal to secant x. Boom. And like that, we can now say, well, log x times by 1 over cos x equals log x secant x. So our whole initial function can be rewritten now that it's been, I'll rewrite it again as sine of log x cosine x. Just like that. Oh, mothers, we are not standing for that. There we are. So secant x. So now let's derive that, because that's going to end up, I do not know what's going through my head as I write this, but this here is going to be a lot easier to derive now, as I find the product rule to be quicker and a lot easier than the quotient rule, which we're going to write here. So dx ub is equal to u dash b plus u b dash. So there's our product rule that we can now write. So let's say let u equal log of x. So log of x times by v, which is secant. Well, the derivative of log is 1 over x. So we can bring the secant x up and put that over x. I'm actually going to get rid of this since we all probably have that in our heads now after using it quite a bit. And now we add now secant, the derivative of secant x, as we did on, well, we used the derivative of secant x in yesterday's video for integralidae. That's going to equal tan x secant x, and well, u stays the same on this side, so that becomes log x. And here we can now, that's right, I ended up bringing secant x out here, because we have a common factor there, just to simplify it. And I believe this is as far as I could get it. However, if you guys got it further, please let me know in the comments how you did it, because I would be interested in knowing. Now, tan x log x. Yep, I believe that there. I'm going to check that against the answer I got earlier, because log x, see, I did check that answer earlier, so I know it is right. And here we are. So this answer here is right. If you got a different one, let us know in the comments what it is, and we'll have a bit of a talk about it. I'll probably definitely, I want to learn from it if you did it a different way or simplified it better. Maybe you made a mistake, or maybe I made a mistake, and so did SimpliLab. But let's graph this now. That is what I'm really keen for. Yeah, so I'm going to be using Desmos. It's what I use for all my assignments. Once again, I'm not sponsored. I'm way too small to get a sponsorship. As a channel, so you know, this is just software that I actually use, and I wouldn't promote anything that I don't use either, because but this is worth promoting for sure. This is great software. I remember for one engineering assignment, I destroyed Desmos with in that it couldn't handle the function I was putting in, but 9 times out of 10 it can handle whatever. But man, this is insane. So this is what our original function was here. That is crazy. Let's just have a look at what does log x over cos x look like. Let's just make that invisible. Wow. All right. So you can see that the cosine of x down the bottom actually causes the logarithmic function to be repeated here, which is insane in both directions. I'm just like playing around with them to see, whoa. So if you times it by 5, it increases by 5, it seems. I don't even know, these are all assumptions. I'm not proving that. However, let's type in our derivative of the function. Actually, our function actually has an increasing frequency here. I have so many questions about that. Look, it cycles through again, and then the frequency increases with either the It's either a cosine or sine wave pattern. That is an awesome function. I wonder at what point does it actually flip back? Like, I would have thought it would have been infinite. It seems to be like the frequency seems to be increasing in a logarithmic form here. That's just another assumption, but all right, we're doing Perf forever for this video, so I'm going to type in here our original cos x by secant. I should not know what I just typed there, so that should be right. Times by secant x 1 over x times by plus, I don't want to mess up typing this in right now. I feel like that's right. I feel like that's the answer we got earlier. Why is that? Why is this? Yeah, we're good. Wow. What on earth? Oh, what happened to our normal thing? Sine. What was it? K of x, yeah? Equal to that. We'll show that as well. Wow. So the green here is our derivative of the blue function. I don't know what to deduct from this at all. One day I will, because we're doing this every day. Look, it seems you've got these similar points here, but not all the points intersect. I'm sure all math lovers or mathematicians love seeing patterns and trying to figure them out. It doesn't seem as if, look, the what's that called? The turning point here. It doesn't intersect our derivative of the original function at the turning point, which is, you know, a bit interesting. But yeah, well, we're definitely going to be doing this every video. After this video, I'm gonna continue to play around with how this looks. Look, if you times the whole thing by 5, you change the amplitude of the whole wave. What if we put 5 over a log? Oh, you get a decaying function. If you're doing any linear systems in control, man, you'd hate an elevator to run off of a function like this. That would not be very nice. But yeah, well, I hope you guys have an awesome day or night, depending on where you are, and I'll catch you all here for day 19 of Derivative of the Day.